Alright, hey everyone, I'm MG8mer. Today we're going to be reviewing Unit 6 of AP Stats. This unit's very important because it introduces inferential statistics, which is basically just significance tests, confidence intervals, and just like assessing claims made about a population, which is made through either confidence intervals or significant tests. So this one is in particular for proportions, but then if you know this unit really well, you should know Unit 7, like, off the bat. Like, it's just copy-paste, essentially. And then 8 and 9 are different, but they're basically the same idea of confidence intervals and significance tests. Mainly significance tests for 8. I haven't done Unit 9 personally, but Unit 8 is mainly significance tests and whatnot, not necessarily confidence intervals, if I remember correctly. So, I think most people here know what 5 hive is. Again, I've said this like twice before. I'm not going to really go over what this is. You guys should know it by now. Of course, check out the 5 hive website. You know, it's really good. I have to do that plug because this is a 5 hive lecture again. And of course, I have to start. Is this the last unit we're doing? No, hopefully. I'm planning to do a Unit 4 review sometime in the future. But that's high chance, but I'm not entirely sure. So, again, disclaimer, AP is a trademark registered by College Board. It's not affiliated with this. Doesn't endorse 5 hive at all or any of our review sources, but 5 hive, that doesn't invalidate 5 hive's credibility. It's still a good review source, you know, you should use it. But, you know, of course, I have to say, College Board does not endorse this at all. So again, expectations, please be nice to each other in the chat. Please be respectful. When you're helping each other out, don't, like, you know, belittle each other. Everyone's learning, and everyone was learning at some point if you know your stuff by now. So you be nice to each other. Be as engaged as possible, so when I send out a poll or do a question, please try your best to do it and don't just like stay AFK and listen. You have to engage with the material so that you can actually grasp it and learn it. And again, please ask questions throughout the lecture. I'm for now open to as many questions as possible until we start to like get on a time crunch where I might not be able to take questions just to get through the content. So I have to plug this here. Please fill out the feedback survey. If you're gonna leave early, ideally fill it out before you're about to leave, but if you can't, that's no problem. But for the people who are gonna stay, you have to fill this out at the end, and I'm gonna send this out periodically just to make sure that, to remind you guys to fill this out. It's good for me and for the lecturers just to know like how we're doing and what we need to work on, what we need to improve in terms of explanations and stuff. Like, for example, I heard a lot of people complain like I talk fast, and right now I am kind of talking fast. So if I'm talking like really fast or anything, please just tell me. I'll try my best to be slow, take my time with things, and explain as best as I can so everyone understands. And like throughout the lecture, I'll just make sure everyone knows what I'm talking about. And again, like I said, if you have any questions, please ask. So we have a lot on the agenda. There are 11 topics for this unit, but don't worry, we'll go through them all. And they're kind of repetitive, so we'll start out with confidence intervals for one proportion. For one population proportion, I'll explain what that is, don't worry. And then we'll move on to hypothesis testing for one proportion. And then we'll move on to confidence intervals for difference between the two proportions. And then we'll do a hypothesis test for difference of two proportions. And there is one filler lesson, which is basically just about the errors you can make when you're doing a significance test. So type 1 errors, type 2 errors, and we'll go over what those are. Hopefully, don't worry. All of this will make sense very soon. And then throughout this lecture, we'll do mini practice. After some of the topics, we'll do mini MCQs, but not for all of them because there's a lot to get through, and I couldn't find many MCQs. But don't worry, at the end, we're going to do one FRQ, and it's going to be based, and you guys will be able to choose what FRQ we do based on like what we've covered. And then we'll do a quick Q&A. So just a warning, this lecture might go over 2 hours because there's a lot of content, but it might not. But just to prepare you guys mentally, we might go over 2 hours because, like I said, there's a lot of topics to go through. So let's first start off with constructing a confidence interval for a population proportion. So in this kind of scenario, you look at a population and you determine the population proportion you want to estimate. So you determine the characteristic you want to estimate. So for example, like how many people own cell phones or how many people are over 6 foot. And then, like we went over in Unit 3, you take a random sample from the population. You can do this with like a simple random sample using the random number generator. Pick out random people from the population. And then you survey those selected individuals. and then you obtain your sample proportion, which is how many of that sample have the characteristic that you want to determine. We call this the statistic, or in other words, the point estimate we will use to build our confidence interval. So as you can see here, just to double check, can you guys see my mouse on the screen? Just double checking. Yeah? Yes? Perfect. So as you can see here, when you're making a confidence interval, when you obtain your statistic, right, from that random sample, you take that statistic and then you add to it the margin of error. And the margin of error is essentially your critical value times the standard error of the statistic. And I'll go over those really quick in a moment, but that's just your confidence interval. So you add the margin of error and then you subtract the margin of error. And then the range is from what you subtracted from your statistic to what you added to it. And that'll be your confidence interval. So like I said, you calculate the margin of error and then you multiply critical value and then your standard error of the statistic. And this is essentially the estimate of the standard deviation of the statistic from the parameters. So like how much the statistic varies from the parameter on average, which is just the standard definition of the standard deviation. And then the margin of error is simply the amount a statistic is likely to vary from our population parameter, which is basically the true proportion of the population that have the characteristic that we're trying to determine. And then, like I said, the confidence interval is just our statistic that we obtain from our sample minus the margin of error and then also plus the margin of error. So now I'll go over quickly, like more in detail about the critical value. So more specifically, in terms of what we're doing a confidence interval for a proportion, and we're doing it for a one sample proportion for a population. So the procedure name is a one sample Z interval for a proportion. That's just the name. You don't need to know like too much about like what the Z interval means, but that's just the name. The standard error, as we defined before, our formula is simply the square root of the statistic or the sample proportion times 1 minus the sample proportion. So it's the sample proportion times like 1 minus that over our sample size, and we take the square root of that. So our critical value is denoted as Z asterisk or Z star, and it's basically how many standard errors, like we've defined before, how many standard errors you're including in the confidence interval. So you can say like, oh, I want my critical value to be 2 or 3 or 1, but we don't usually do that. It's usually based on the standard normal curve and the confidence level. So for example, let's say you have like a 95% confidence level, and you're basically asking how many standard deviations of the mean lie within this percentage of the data. So like if we take 95% of the standard normal curve, how many standard deviations of the mean lie within that? And then to determine that on your calculator, let me just grab it real quick. You use the inverse norm function. You put your area as 0.96 or 96%, and then for the standard normal curve, you put a mean of 0 and a standard deviation of 1, and you put the tail in the center. So you're trying to calculate that area in the center of an area of, actually it's supposed to be 95, sorry, 0.95, 95%. And then when you calculate, when you use the inverse norm, you'll get like what the left value and the right value in the center are. And so when you do that on the calculator, you'll get negative 1.96 and 1.96. You take the positive value, and that'll be your critical value, or in other words, if you're using a 95% confidence level, your critical value, or how many standard errors you're including in your confidence interval, will be 1.96. So I'm going to turn on my webcam real quick and just, what's the difference between left, center, and right? So left is basically the area on the left side of the distribution, not in the center. So you put a specific value and then you calculate the area on the normal distribution to the left of that value. Right is simply to the right of that value, and center, you essentially, well, on the when you're calculating for normal CDF, when you're calculating area, there is no option for center. But when you're doing inverse norm, when you're giving an area, you can make it so that the area is in the center, and then it'll give the negative value and then the positive value that's attributed to that area. So let me just show you how it would look like on the calculator. Give me a minute to turn on my webcam. All right, you guys can see this, right? My inf norm doesn't have a tail input. Wait, let me see if mine does. Might be a problem with your calculator, which would be annoying. So you can see here on your TI-84, this is for TI-84, you click second, and then you go to distribution. Once you go here, you scroll down to the option that says inverse norm. You guys can see this, right? Just to make sure. Kinda. Yeah, it's a little bit not the best. Sorry about that. Bring closer. Oh, is this better? Oh, it stopped working. Whoops. I don't know why my webcam is really bad. It just stops working for some reason. Let me fix that. Wait a minute. Oh. My webcam completely died. Oh, that's not ideal. Give me a minute to fix that. Rip. No, I'll fix it. I'll fix it. Don't worry. That's complete. Oh! Yeah, this is not how it's meant to be. I don't know why it just dies like this. Yeah, second, VARs 3. So it varies on the calculator, depending on that. But yeah. I'm really sorry about this. This was not meant to happen. Please work. I beg you, work. Virtual. Please work. I don't know why it's not working. This is really annoying. Sorry, why isn't it? It's completely not working. This is terrible. Still black. Wait. Should work soonish. So for the area, why do you put 0.96? Oh, sorry, that was just a typo. No, when you're doing 95% confidence level, you put 0.95. That was just a complete typo. That's my bad. That's not meant to happen. You're not meant to do that. It's not like 0.01 extra. That would be really stupid. That not make sense. This didn't happen last time. Oh, yes. Okay. No! It lagged again. Hopefully it doesn't do that. Okay. And it's still lagging. Oh my god. Hold on. Yeah, it's not visible right now. Oh, okay. What? No. I don't know why it just... Sometimes it starts lagging, sometimes it doesn't. It's really inconsistent. Why does it not work? Oh, man. I'm really sorry about this. This was not meant to happen. We can just move on. I don't have to show you guys on the calculator if you, hold on. I'm just gonna input for now. Maybe you can just talk us through it. So, yeah, that's a better idea. So sorry about that for taking up a lot of time. That's completely my bad. I'll fix it in a bit. But just the way you do it is, on your calculator, you click second. And then what you do is you click the VARs button, which will take you to the distributions. Once you're at the distributions, there's like normal PDF, CDF, inv norm. But then from VARs, you have to click on inv norm because for one sample z interval, you're basing it off of the standard normal curve. And when you're using inverse norm, you're getting the value that's attributed to a specific area on the curve, right? So then you click inverse norm. Once you click inverse norm, you can input your area and your mean and that. So for the mean, you input your confidence level. So in this case, in our example, we're doing 95. Our mean is 0, and then our standard deviation is 1, as is on a standard normal distribution. And then for the tail, you can either put it towards the left, which will most likely give you the negative value. So let me just test that. Actually give me the positive value. But like regardless, if you use center, you use the positive value. Right? Wait, actually, no. It's supposed to be, if you do 0.96, give me a second. Yeah, mine doesn't have a tail. That's not supposed to happen. It's supposed to have the tail button, so that's a problem on your calculator. I'm really sorry. That's really annoying. Wouldn't normal CDF work? Not really, because normal CDF is for area, not for just subtract and divide by 2. So when you do inverse norm and you use center for the tail, you'll get a negative and positive value. For your critical value, you use the positive value. Does that make sense? For the people who can actually use it on their TI-84, if you have one. But did that make sense? Yeah? I'm going to now try to get my webcam to work. Actually, I'll try to get it to work when I need to. Right now, I don't think I need to use it. So right now, for the time being, we'll just go with no webcam. So I'm really sorry for taking up a lot of time, but let's just move on. I don't want to waste too much time. So then after that, we have to go through the conditions. These are the steps for inference for building A1. It auto does center tail if there isn't a choice. I believe so, yes. I think that's what it does. If it does that, yeah, you just use the yeah, use table. Table should work just fine. I'm not too familiar with table, but calculator is more ideal, but yeah, table would also work. But yeah, table would definitely also work. But yeah, it's not the best. The calculator is much faster. But yeah, that's really annoying that it doesn't work on your calculator. I'm really sorry. But anyway, so when you're building a confidence interval for one proportion, right? First, you have to state the population parameter that you're trying to estimate. So like, we're looking to estimate the true proportion of people who wear green shoes, for example. And then you have to state your confidence level. So it's like, we're looking to estimate this at 95% confidence, 96%, 97% confidence, and we'll go over the interpretation for confidence level in a moment. Then the second thing, you have to name your inference method. So this is for the general steps for any inference, but for us, we determined that last slide. So you have to say, we're going to do this using a one sample z interval for a proportion, and then you have to check the conditions. You always have to check the conditions unless stated otherwise, unless it says assume conditions are met. But not often, more often than not, you will have to check the conditions yourself. The first thing you have to check, did they use a random sample? If it's stated they selected a random sample to do this, yes, you're good. You're good to go. They used a random sample. Or if it's a randomized experiment. So sometimes the situation is not necessarily a random sample, but they're doing a randomized experiment to determine a characteristic of like maybe the people, for example, who got treated by some kind of medicine. We went over a lot of experimentation principles in Unit 3. You can watch the lecture video for that later. But then you also have to like check the second condition, which is sampling without replacement. When sampling without replacement, the sample has to be less than or equal to 10% of your population. But the thing about this condition, are confidence intervals guaranteed to be one of the FRQs? Not necessarily, no. What's guaranteed is that you'll most likely do something related to inferential statistics. You'll most likely do a significance test, but sometimes you might get asked to build a confidence interval. Sometimes on the same exam, you might get a question that construct a confidence interval and do a hypothesis test, or you might have to do both at the same time, kind of. You might have to like do a confidence interval or do a hypothesis test. You might have to do both at the same time. So, yeah. So it's not guaranteed, but it could be. It could be both, or it could be one or the other, right? Does that make sense? Okay. So, for this condition, for sampling without replacement, you don't actually have to check this if it's a randomized experiment. So, if you're doing an experiment, if the situation is an experiment, you can safely assume that the experimenters already checked that the sample is less than 10% of the population. You don't have to check that condition. You don't have to say, oh, we're not checking this condition because of this. No, you're exempt from checking it if it's an experimental situation. But if it's not, if it's just a sample, you've got to check this. Then will you get penalized if you check it anyway? I don't think so, but it's just a waste of time when you're very limited on the AP exam. You know, so you don't got much time. So if you don't have to check the condition, don't, because you don't need to. Alright, sorry, I was just drinking water. Anyway, the second condition, the second aspect, you first check for independence. These are for independence. You then have to check for the normality of the sample proportion sampling distribution. You just have to make sure that the distribution of your sample proportion of like the standard error and whatnot, you have to check that it's normal. The way you do that is that the number of successes, which is the sample size times the sample proportion, is at least 10. So when you multiply those, is the value at least 10? It's 10 or greater. If it is, that's the first part of the condition met. The second one is the number of failures at the number of failures, which is simply the sample size times 1 minus the sample proportion, which is just simply the number of failures or the chance that the person does not have a specific characteristic, is also at least 10. And by checking this, you ensure that the sample size is large enough, and therefore the sampling distribution will be normal. So you have to check this. Then the third step is you have to do your calculations. You can do this by hand or using the TI-84 one prop z int function. And because like the TI-84 has this really helpful function, you don't necessarily have to go through the steps where, first you first calculate the margin of error and then plus minus that from the statistic. You can do all of that using your TI-84 one prop z int function. So I'm just gonna try to get my webcam to work. If it's not gonna work, do we have to check if the total size is greater than? No. This is Unit 8. You don't have to check if the sample is 30, because you do small sample sizes when it comes to means. When it comes to a sample mean, you do smaller sample sizes, which is why you have to check if if it's at least 30, to appeal to the central limit theorem, which is essentially that if a distribution is not normal, but you select a sample from that distribution that is greater than 30, then that distribution will be normal. That's Unit 5 and Unit 8 related. You don't have to worry about that here. You just have to worry about these conditions. So don't worry about checking this. Don't worry about that. So to use the 1 prop z function on your calculator to build a confidence interval, of course, when you're doing the FRQ, you have to do the state and then the planning procedure to check the conditions. But when you're doing the calculations, if it's on an FRQ, don't bother doing it by hand. That'll take too much time. So the way you do this is, if my webcam doesn't work, I'm going to just describe the steps on your calculator. Oh, it was working for a second, but then it stopped. That is fantastic. Okay, let me try again. Still black. So stupid. I don't know why it just doesn't work. Why it doesn't want to work. It's so stubborn. Like, my webcam has this problem. It just stops working. Oh! And it stopped working. No. It's so stupid. Nope. Last time, so you don't waste too much time, because it'd be nice if I can show you through the webcam. Because that's very ideal. Because, you know, it's more, you know, hands-on that way. Okay, I can't get it to work, I'm sorry. So the way you do it on your calculator is, you have to click stats, the stat button, and then you have to go to the tab where it says tests. So the third tab that says tests, and then there are a lot of tests you can use, but don't concern yourself with any of them. You have to go scroll down until you find the thing that's called 1 prop z int. Okay? You go to 1 prop z ints, click that, and then there you'll be able to input various things. So you first input your sample size. You first input your x variable, which is how many of the people in your sample had that characteristic that we're trying to measure. So let's say you grab the sample size of 500. Let's say 200 people wore green shoes. Let's say 200. X is 200. And then your sample size is 500. Yeah, thank you to everyone who's like putting the steps needed to check these things. This is very useful. That's awesome. And then your sample size will be, let's say we said our sample size is 500, and then all you have to do is put your confidence level. Let's just say we're using a C level of 0.95 or 95% confidence level. When you do that, you do 200, let me input them into my calculator, 500, 0.95, calculate, and then you'll get your confidence interval. So if you did it right, your sample proportion is 0.4, and then your confidence interval is something like 0.357 to 0.443. 0.44294. If you guys tested that, if you guys followed me on the steps, did you guys get that confidence interval? Yes? Perfect. And then lastly, after you do your calculations, you have to conclude and interpret and everything in context. So once you have your confidence level, we'll go more over on how to interpret in 6.3, but you have to conclude and interpret in context. So what's neat about our formula for margin of error is, like I said, it's the critical value times the standard error, and this is less than or equal to the margin of error. So when you're trying to solve for sample size, often on an MCQ or an FRQ, you're often asked to solve for n, or the sample size. What's the sample size? What's the smallest sample size that will get us this margin of error? So they'll give you the confidence level, and if you're given the confidence level, you can determine the critical z value, which is determined using our inverse norm function, as we went over earlier. And then you have that, and then you might ask, what do you put for sample proportion? If they give it to you in the problem, you just put it as is, but often they won't, and so you're just gonna have to use 0.5, and we do this so that we find an upper bound for the sample size that results in the given ME. So we're trying to do the worst case, which is 0.5 times 0.5. That'll be the largest value. 0.5 times 0.5 is 0.25. And then what you do is simply, when you're given the margin of error, divide by the critical z value. Square both sides to remove the radical. Multiply by n, and then divide by whatever the quotient between the margin of error and the critical z value is, and that'll give you your sample size. So when you multiply these, that should give you your sample size. So in essence, you just rearrange the formula to solve for n. This is basic algebra. You probably all learned this, and you'll get n. Does that make sense? So that's basically 6.2, essentially. Does anyone have questions? Does this make sense? Okay, I'll move on. Seems like people understand this. Okay, so 6.3, this is a short lesson. This is just justifying claims based on a confidence interval for population proportion. So you can justify claims based on the confidence interval and stuff like that. It's like, oh, if like for example, if your confidence interval, like we said, is 0.35 to 0.44, if it asks you like, oh, 0.5 is not our interval, so it's not likely that that is a value, the possible value or something like that. So you basically, depending on the situation, use your confidence interval to draw conclusions. So this is kind of contextual. I can't go over every scenario, but you kind of get the idea. You can just justify claims and whatnot. So confidence intervals / level, basically these are just some interpretations. So the confidence interval either contains the population proportion or it doesn't. There's not like, oh, there's a 95% chance it's in there. No. It's either a 100% chance it's in there or it's a 0% chance it's in there. There's no like in between. It's either is or isn't in there. And then the interval will vary based on random sample data. So it varies because when you select a random sample, the sample proportion will vary due to like the standard error of like the proportion statistic. So it might be like your sample proportion might be 0.5, then second sample 0.4, 0.6. So it varies. And the confidence interval is simply, the way you interpret it and conclude it when you're doing an FRQ is, we are C% confident that the interval from the lower bound to the upper bound captures the true proportion of, and then you put the context given the problem. So it captures the true proportion of the amount of people that wear green shoes, for example, or the amount of people that wear green shoes in New York, or something like that. So the context can vary. Then the confidence level you interpret as in repeated random sampling. So when you repeatedly random sample with the same sample size. So if you repeatedly random sample with a sample size of, in our problem, like let's say 500, approximately, let's say our confidence level is 95% of the confidence intervals that we construct based on the sample that we get will capture the population proportion. And this is as defined in the CED. So that's the interpretation. This is really important because sometimes they'll ask you MCQs, what is the interpretation of the confidence interval, or what is the interpretation of the confidence level? They'll give you that, and you have to like interpret it correctly. So often people will say interpret this incorrectly. So this is the true correct interpretation, and this is the true correct interpretation of the confidence interval. And like I said, you can use confidence interval to prove / disprove certain claims made about a population. Same way you can do in a hypothesis test, but that's a little bit different, right? So, I see some people are typing. I'll answer your questions. Will it be specific on which one to interpret on the FRQ? Elaborate. What do you mean? Sorry, I just want to understand your question. Oh, like you mean like which one? Oh, interpret the confidence level, interpret? Yes, it'll be specific. No, but like whenever you're asked to construct and interpret a confidence interval, always write the interpretation for the confidence interval that you make. You don't have to write for the confidence level unless they ask. That is more of an MCQ thing. They might give you a confidence interval, and then you're asked, what's the interpretation of the confidence level in this scenario? I learned a different way to interpret CI. Same word, but different structure. Yeah, it varies, but I like that structure. You just say, we're 95% confident of this, that it captures the true proportion from this to this. That's the structure, but it can vary. The structure, it depends, based on how you learned it in class, but it's all the same idea, right? So confidence interval width. The width of the confidence interval decreases with increasing sample size. So the relationship between the width of the confidence interval and the sample size is this. So you can see here they're inversely related. So as the sample size goes up, the confidence level interval decreases. What that means is it becomes more precise. So when you increase the sample size, you narrow down your confidence interval so that you have a more narrow and precise estimate of where your true population proportion is. So you could have a very high confidence level that captures a lot of like the possible population proportions on your standard normal curve. But if your sample size is really low, that confidence interval is going to be really big. That's not going to help you determine like what the population proportion is. Because if you just sample everything, you're not going to really get a good idea. So it's like saying, oh, the temperature will be below 200 degrees today, at least, because, well, it cannot get to 200 degrees, I hope. So like if you say it'll definitely be below 200 degrees, technically you're not wrong, but you're not giving me a true estimate of like the temperature and stuff like that. So that's not really helpful. And again, the width of the confidence interval increases as confidence level increases. So when you increase the confidence level, like we said, the width of the confidence interval increases. And it's twice the margin of error often. Right? So now we're going to do some practice MCQs. 2 of them, because like we're not going to do as many later on. We're going to try to get through the content. So we're already at like half an hour. So like it did take a while to go just through 2 topics. So you see there's a lot of things we have to go through and just to make sure you guys understand and stuff like that. So just, does everyone understand like the content from 6.2 to 6.3? Just making sure. Yes? Yes. For the people who are not sending messages, please make sure you send, because I need to make sure like if you don't have any questions, like please feel free to ask. Like I said, like we have time to ask questions. For the people who are leaving early, I'm going to send this for the second time. Please, 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 please fill out the lecture feedback form. It's very helpful for me to know if I'm explaining too fast, or if I need to slow down, or if I need to be like less yelly and stuff like that. So like this is really helpful for me. Of course, like you technically don't have to fill it out, but it's really useful to me. So with that out of the way, now let's go into the MCQs. So you might take a while on this. I'm going to give you guys like 2-3 minutes for this. Based on a survey of a random sample of 900 adults in the United States, journalist reports 60% of adults favor of purchasing. Which of the following is closest to the level of confidence? If you need a hint, I'll give it to you. There is a way you solve this. But like, I recommend just, go ahead. Bro's going to do confidence levels for the survey. Now, yeah, perhaps. Like, how many people say, oh, the lecture was insane, construct a confidence level. The true proportion of people who said the lecture was, that's an example, I guess. But, for everyone who's in here, please, oh, right. Oh, yeah, I should make a poll. This is not an FRQ, this is an MCQ. So, can someone make a poll, please? A to E. Thank you, Dragonfire, very useful. So, like, when everyone gets the answer, hold on, I have this on my laptop. Let me just make sure what the answer is, just to see, like, before I reveal the answer, who's on the same page and whatnot. Interesting, that's the answer. Okay. While I'm waiting for you guys to answer and whatnot, while I wait for you guys, a majority of you to answer, I'm gonna try to get my webcam to work, because it is pretty would be pretty darn useful if my webcam works right now. It's pretty important right now for it to work. If it doesn't work, we can just resort to using an online whiteboard, because I'm gonna want to write stuff down for this question, because you have to solve it by hand. But anyway, it's still really buggy, annoying, stupid. I'm really annoyed. I don't know why it just doesn't work. Oh, nothing happened. Oh, someone already solved. Wow, good job. It's not even showing up. I don't know why it just stops. It was working fine in the previous lectures. I don't know why it just stopped working. I mean, I'm gonna give you guys more times just so that a lot of the people here can respond and stuff like that. It's best if you guys aren't AFK and reply to the poll, as always. Okay. Let me just get a whiteboard ready. Online whiteboard. So, like, because I don't think I'm gonna get my webcam to work anytime soon. Which is RIP. Rest in peace. This is really kind of annoying. But we move on. We don't wanna linger too much. Oh wow, my PC is really hot. Oh, that is bad. Okay, let me lower the temperature level. So yeah, we're gonna try to do this on the whiteboard, because it's ideal if I actually try to get this to solve this by hand. Okay, whiteboard, free online whiteboard. Yes, and I have the lecture slides open in the background. All right, cool. That's great. All right, let me try to one last time to try. Nope. I don't think I'm gonna get it to work. Sorry, guys. Oh wait, it's showing up. Wait. Pray that it works, guys. Please. No, it stopped. Okay. Okay. One last time. Come on. Don't be shy. Please work. Alright. Alright, I'm not gonna get it to work. Let's see how many people replied on the poll. Not gonna lie, I don't know how you would do this without a table. Yeah, or you need to use your calculator, low key. Let's see what people have. Oh, it's kind of mixed. Alright. So, let me reveal the answer, because a lot of people replied. The answer is B. So, one person voted B only. This is a little bit of an annoying problem, so we're gonna go over it together. No, don't worry, we're gonna try to go over it. I'm gonna try to solve it. If I can't, Dork, you can help us out. But I'm gonna try my best to, okay. You guys can see this? Can you guys see my screen here on the whiteboard? Yes? Okay. So if we go back to the lecture, we see that our sample size is 900. So let's just write that down. Sample size is 900. Let's just write that. So you can see I'm writing stuff down. I'm just having the lecture slides open. So the proportion is 60%. So we're just writing all the crucial details of the problem down. And then the margin of error is yeah, I know. I'm just like I'll show you in a moment. So the margin of error is 0.027%. So you guys can see this, right? I really apologize for my atrocious handwriting. Forgive me for this. But like, yeah. Anyway, so we know the formula for the margin of error is, we know that it's just the critical z-value times the standard error. So can anyone just real quick tell me what's the standard error for a population proportion or for a sample proportion? What's the standard error? Just, you know, just wanting you guys to also solve along with me. Square root p. Perfect. Nice. Yes, that is it. Also, we're kind of we're like, yeah. All right. I don't know the exact number. All right. So anyway, so it's just the sampler proportion times 1 minus p over n, which is greater than the margin of error. So that's just, let's just write that 0.227. So we know when we're trying to solve for the confidence interval level, we're trying to solve for this first. We want to get our critical z-value so we can use that to obtain the area on our standard normal curve. So we were trying to solve for this. So let's just plug in our values real quick. So automatically we're going to divide this by the margin of error. So greater than or equal to 0.027 over that P1 minus sample proportion over the sample size. So now let's just plug our numbers in. Let me grab the eraser real quick. And then let's just plug in our numbers. It's 0.060, and that's just, here it'll be 0.60. We just plug that in. Our sample size, like we said, is 900. And then we just solve for this. So can someone grab out their calculator and just calculate this real quick? Just spew out the exact value, preferably. What's n? 900. 1.653. So that number looks familiar. So when you do a lot of these confidence interval stuff, you'll start to recognize these numbers. You see 1.653 looks very familiar, looks kind of familiar, like we've seen this number before. It's kind of a common number. So this will be our critical z-value, most likely. 1.653, something like that. So now we use that on our normal CDF function. Because we're trying to get the confidence level, we're using normal CDF. We're not getting a value, so we don't use inverse norm. So again, the procedure will be the following. So second vars, you go to your distributions, you go to normal CDF, and then for your lower, you put the negative of that critical z-value, and the upper, you put the positive of that critical z-value. Mean 0, standard deviation 1, what you'll get is 0.90166. So that's how you get your 90% confidence interval. So when we go to our calculator, so let me just write it here. So you use the normal CDF function, because whenever you're given these kinds of problems, are you trying to calculate for area or a value for a normal distribution? If it's a value, you use inverse norm. If it's for an area, you use normal CDF. So The lower will be the negative of this, so negative 1.653. The positive will be 1.653, and then the mean is 0, and then it's 1. When you're doing these kinds of problems, if you're asked this on an FRQ, you have to, of course, say that this is your lower, this is your upper, so you have to annotate this. When we do that, we get 0.90, and that means our confidence level is 90%. So we go back to the lecture, it is indeed B. Does that make sense? So you just got to use the formula for the margin of error, solve accordingly, and you get that. Why does your lower have to be negative 1.63? Because you're trying to calculate the area between the negative of our critical z value and the positive. So remember when we're trying to do inverse norm to get our actual critical z value? Remember what you notice is the fact that you gotta, like, for the center, you put, like, when you do the center, you get the negative of the critical z value and the positive. So when we're doing the inverse of that to try to get the actual confidence level, you notice that you have to first put the negative and then the positive to get the actual area. Because if you just put negative a very large number, you won't get the true confidence level. Right? Will it always be center? Usually, but I believe if you put the critical z value to the left and then you just calculate the area to the left, you should get the same value. But center is always ideal. But let me just test real quick. If you do normal CDF and you don't do center, like let's say you say your upper. Now actually, when you're doing normal CDF, you have to do lower as negative 1.653 and upper as 1.653. But when you're doing inverse norm, you don't have to necessarily use center. I think it can work if you do like left, but then you put like your upper value as 1.653, and then you calculate to the left, you should get the same value. Does this make sense to everybody? Did that explanation make sense? Oops. Explain this again. Sad? Why sad? Dragonfire, why sad? Okay. Let's go back to the whiteboard. It's not showing. I don't know why. Okay. Oh, I closed it out. Answer was shown. For a split second. Not for long. Okay. I don't know why the whiteboard's no longer working. There we go. Okay, back to the whiteboard. When do you use CDF and inverse norm? You use CDF when you're calculating the area of the distribution. But then you use inverse norm when you're trying to get a value. So you input the area you have, and then based off of that, from that area, what's the value that is to the right of that or to the left or in between those? So let's say you're given an area in the center and you have to determine the maximum value to the left or right. So if you do center, you get the value on the left and on the right. So you'll get the negative value on the left and then the value on the right. Right? But then when you're doing CDF, you're trying to calculate an area. So you put a number on the standard normal curve and then you choose your tail. So if you choose left, not gonna lie, I don't think I can well. Wait, hold on. So like when you're trying to do the area, you pick a number. Let's say you do the lower as 1.653 and then your upper as another value. You're calculating the area that's in between those two values on a standard normal curve. And then when you click it paste and then you put your mean as 0 and 1 that's for a standard normal curve, you'll get your area. Right? That's for CDF. But the inverse norm, you're given an area and then you try to determine the value that's at the end of that area. So like where does that area end? So like it's kind of the reverse process. So for normal CDF, how we're like trying to figure out the area when we're putting in a value, we're trying to figure out the value. Why is it centered without tail? What do you mean? CDF and inverse norm are opposites. Exactly. They're opposites of each other. So you do the opposite processes with them. Thank you for explaining that, Dragonfire. Like, if not negative 999 or 999. Are you referring to normal CDF? Yes? So when you're using normal CDF, like I said, you're trying to calculate the area between one point and another. So you put your lower value, let's say you put like something like 2, and then your upper, you put 5, for example. And then when you put the mean of that normal distribution and then the standard deviation, if you put a mean that's not 0 and then you put a standard deviation that's not 1, you'll get a distribution that's approximately normal. But then when you click paste, you'll calculate the area between that value and the other value. So the area will be not 1, but it'll be like a percentage. So what percentage of the distribution is covered by starting out from that value to that other value? So what percent distribution covers that? Does that make sense? What are you not understanding? Why is the cutoff at negative 1.653 and not all the way to the left? So when you're doing a critical z-value calculation, you have to put the cutoff as the negative value of that critical z-value, and then the upper cutoff as the positive, so that you can actually get your confidence level. Yes, exactly. You're trying to get the area at the center. If you do it to the left, you won't get the proper confidence level. You won't get the proper confidence levels. You have to get, because between the two z-crit values, yes. Exactly. So the z-critical value is basically, like we said, how many standard errors, as we explained before, you're including in your confidence interval. Right? So, like, if the mean is 0, the critical z-value is 1.6. That's 1.6 standard deviations away from the mean. And then your confidence level is simply what is in between the standard deviation, the negative one, and then the positive one. So, like, represents margin of error, yes. So when you're doing standard error, it's basically just the standard deviation, like how much on average does a sample proportion vary from our parameter. And then the margin of error is how, like, let me just check the slides again. Switch to the slides. If you go here, we go to our definition of confidence margin of error. We defined it as
Muted. Unmuted.
Oh, sorry, I muted indefinitely, my bad. But the margin of error is the amount a statistic likely varies from the population parameter. So it's like plus minus, like we said here. Right? I hope that made sense. Because we have to move on soon. We're spending quite a while on 6.2 and 3. Okay, yeah, thank you. Is everything cleared up to everyone? Yep. Alright, I'm going to move on, like, because we're dwelling a lot. So we're done with one population. Oh, wait, we forgot to do the second MCQ. I think in the interest of time, I'm going to skip the second MCQ and we're just going to jump into the content. Is that fine to everyone? Because, like, we spent a lot of time explaining this. If you guys want to do the second MCQ, that's fine. Because I allocated that we're going to probably spend more than 2 hours. Yes? Okay, I think we should move on because I want to get to the FRQs. And there's a lot of content. So just, we're going to get through this, guys. I promise you. Okay? So now, wait. This slide is supposed to be here. Anyway, whatever. So now we're transitioning from confidence intervals into something called hypothesis testing. So whereas confidence intervals, you're estimating a true population proportion by constructing an interval using a sample statistic that you obtain through random sampling and surveying. Now we're testing claims or hypotheses, if you will, made about a specific population proportion by assessing the statistical significance, which simply means there's a low probability of it being due to chance, of an obtained sample statistic. So we're testing the claim of, let's say, the population proportion is greater than this, or something like that. And then you test that by obtaining a sample statistic, and we see through our hypothesis test how unlikely that sample statistic is. We see, like, the statistical significance of it, and we'll go over more about what that is. Oh, hi, Nip. Welcome. So, setting up a test for population proportion. We're not going to go over calculations. So 6.4, 6.5, 6.6 cover the same concept. Hi. We're covering all the same concept. 6.4 is setting up the test. 6.5 is doing the calculation. 6.6 is the conclusion. So we spend a lot of topics on this just to get you guys to understand hypothesis tests in general. So let's go. Let's do this. So when you're comparing different kinds of hypotheses, you have two kinds. You always start out with the null. The null is the given or assumed case until proven otherwise. So it's just the given or assumed case, the case that you assume until it's proven otherwise. So think of it as innocent before guilty. So you always assume that this value is true. You always assume the null hypothesis is true until you test otherwise. The notation for it in terms of a sample proportion is H subscript 0, and that the true population proportion is equal to the P of 0. And P of 0 is the null or hypothesized or the assumed population proportion in question. And this will often be the claimed population proportion, or this will often be like what the claimed population proportion is. So they're trying to claim that, oh, we know that it's 0.4, however, we found a sample that says it's 0.6. Is this statistically significant? That's what we're trying to figure out. The alternate hypothesis is the unproven belief or claim that we would like to collect evidence to prove or disprove. So it's always either one-sided notation. A one-sided notation is either that the alternate hypothesis, the true parameter, is either less than the null or hypothesis assumed population proportion, or it's greater than that. And then two-sided notation, it's that the population proportion is not equal to P of 0. So the assumed, yeah, I know, it's great. So like, it's always like, it's not equal to the null or hypothesized assumed population proportion. It's not equal to that, so it can either be greater than that or less than that, and you choose the alternate hypothesis depending on the context. And more on, we're gonna go more over like the first population proportion not being equal to the second in the future topic 6.10, 6.11, which is quite far, but bear with me. So the procedure name for a hypothesis test for a one population proportion is it's called a one sample z-test for a population proportion. And then the null hypothesis states a single value for the population proportion. A single value, this is the population proportion, and there's no difference or effect. So it's always one value. It's never like, oh, this is less or greater. No, it's equal to this. That's our no. We always go into a hypothesis test assuming that the population proportion is a specific value, right? So we're gonna go more over the conditions and the 4 steps of inference for a hypothesis test. But we're just gonna, for now, go over the second step, which is naming your inference method and checking the conditions. For your conditions, it's very similar to last time. You have to check it's a random sample, randomized experiment. You need to check that the sample is less than or equal to 10% of the population. Remember, no need to check if it's a randomized experiment as we went over before. And then you have to check that the sampling distribution of our sample proportion, of our assumed proportion in this case, where like we assume the null hypothesis is true, P equals P of 0, which is the number of successes of that assumed proportion and times P, plus the number of failures, which is just this, which is 1 minus. Yeah, we got locked steps. Yeah, I know. You'll see them later, okay? I put the lessons, you're gonna see them, don't worry. And then at least 10. Both these have to be at least 10. So these are the conditions you have to check before proceeding with the hypothesis test. Right? How laggy is this? Let me see the temperature of my laptop real quick, because that might not be ideal. Because it's, I don't think it's too hot. I'll move on, just want to check. It's not good. Anyway, we move on. So now, we're gonna go over interpreting p-values. In other words, this lesson is just checking the conditions. Well, no, checking the conditions, doing the calculations for our hypothesis test. So did 6.4 make sense to everyone? Did that topic make sense? Yeah? So, before I go on, I just want to send a feedback survey one more time, because I see some people are leaving and re-entering and stuff like that. So just want to make sure you guys fill out the feedback survey if you're planning to leave early and stuff like that. Just make sure you guys fill that bad boy out, please. Anyway, so now we go over to the calculation aspect of things. So now we grade out these steps because we've gone over them. We're gonna go over these because these are more conclusionary steps. The first one you kind of can go over in 6.4, but it has significance level, and we don't get to defining the significance level until 6.6. So now you do your calculations. You can either do those by hand or by TI-84's one prop z test function. So to get to the one prop z test function, you simply do second. No, actually, you don't do second. You do stat, tests, and then you go down to one prop z test. And then what you do is you input your null hypothesis, your x, which is how much of the people in your sample have the specific characteristic you're estimating, and then n, which is the sample size, and then you input your alternate hypothesis. So if the true proportion is not equal to our null hypothesis, if it's less, or if it's greater. So you input that, and then you click calculate, and then it'll give you your z statistic. We'll go over what that is, and it'll also give you the p-value, and we'll go over how to interpret that soon. So for the hypothesis, that's the first step. You have to calculate your standardized statistic, or the z statistic for proportions, you call it. So you calculate this by taking your statistic. So your statistic, again, is the sample proportion that you obtain. And then that's minus the parameter, and your parameter is your null hypothesis, your null proportion that you assume to be true that we defined at the beginning. And then you divide that by the standard error, which we've defined earlier for a proportion as this. And then the z statistic is essentially where our sample proportion that we obtain from our sample lies on the standard normal curve. So you have a standard normal curve, you obtain a sample, and you standardize that sample proportion to a z statistic, which will be where it lies on the standard normal curve, and then you use that to calculate the area below or above, it depends, and that'll be your p-value. So we're just going to go over that. So if the alternate hypothesis is that the true parameter is greater than our null hypothesis, than our null proportion, then we calculate the area under the standard normal curve at or above the value of the test statistic that we obtain. If it's less, we do at or below the value of the test statistic. We calculate the area of that. And if it's not equal to, so if we're saying that the true population proportion is not equal to our hypothesized proportion, our assumed proportion from the beginning, we take the combined area under the standard normal curve at or below the negative absolute value of our test statistic, and at or above the absolute value of our test statistic. And the area that we obtain from doing these things is our p-value. And assuming the null hypothesis is true, this is simply the probability of obtaining a test statistic that is as or more extreme than the observed test statistic that we calculated, right? And to get our p-value, we calculate the area on our standard normal curve. So we use normal CDF of that, like we went over very thoroughly. You go to second, vars, and then you scroll down to normal CDF, and then you set, and then depending on what you do, if it's at or above, you set your lower value to be the z statistic, and then you set the upper to be a big value. So we're trying to see the entire area above that z statistic. However, if it's the area at or below, you set the upper to our z statistic, and then you set the lower to a big negative value. But then if you're trying to do the combined, you can do either above or below, and then multiply that value by 2. So that'll give you the combined area. So that's how you do it by hand. But like I said, it's much easier to do one prop z in, so I'll go over with that with you guys in a moment, because that's much easier. So here's just a summary of what we went over. So one-sided test. If we're trying to say that the population proportion is greater than our null, we do the z statistic above. And then if it's like this, we do below. And then if it's not equal, we multiply by 2. So if it's the combined area at the negative value below, and then at the z value, the positive value up. So we're gonna quickly do the MCQ, but before I want to just demonstrate. Let's just try to get my webcam to work, ideally, because I don't like having to. Okay, hold on. Let me turn off this in case you guys just see my face. I preferably don't want to show my face. Some of you guys know what I look like, but I want to keep this closed. Okay, still seemingly not working. I'm gonna get it to work for a little longer, and then we're just gonna not go on for much longer, because I don't want to waste too much time on this. Okay. So I'm trying to get that to work. OBS virtual. Oh, and it's stopped working. Alright, I'm not going to try to get it to work for much longer. So the way you do it on your calculator is you go to stat, tests, and then you go to one prop z test. So that's what it's called. It's one prop z test. And then you input, like I said, your null hypothesized value from the beginning, your x, which is how many of your sample had that characteristic we're trying to assess the claim about, your sample size, and then your null hypothesis, which is in prop, and then you click calculate. And then what you'll get is your p-value, which is the area as we've described here, And then we get our sample size, and then you get your z statistic, which is usually like 0.2 point something or 3 point something. So whenever you're doing an FRQ and you do the calculation part, you have to write the z statistic and then also the p-value, of course, because that's what you're trying to do. So now we're going to just do a quick practice MCQ. So an experimenter conducted a two-tailed hypothesis on a set of data, and he obtained the following p-value. We've went over the interpretation of p-value. You guys should know this decently. If the experimenter had conducted a one-tailed test on the same data, so instead of a two-tailed test looks like this. If he instead did a one-sided test, like this or this, as you can see by my cursor, which of the following would be true about the possible VLs that the experimenter could have obtained? So someone make a poll, please, and then you guys just answer the MCQ. Dragonfire, could you make the poll? Or someone else, ideally. You guys there? Someone gonna make the poll, or or am I gonna make it? I'll do. Okay. Okay, thank you, Dork. Thank you so much. Goats. Yes, indeed. Alright, I'll give you guys more time to answer. But are my explanations making sense? Like, is this, like, lecture making sense overall? Are you guys understanding things? Yeah? You the goat, thank you. It's good. Yep. Fantastic. Awesome. That's great to hear, guys. Kaboom, are you still with us? And Tater. And 5 something something for that matter. Are y'all still with us? Are you guys following? Okay. Alright. Okay, 5 of you guys voted. Let's see what we're doing. Awesome. We're all on the same page. It's D. The answer is D. Do you guys want me to explain, or do you guys understand why it's D? Please? Explain? Alright, let's do it. So when you're doing a two-sided test, like we said, we're doing this. So like as I said before, you can simply obtain the result of a two-sided test by conducting a one-sided test, which is you get the area above the Z statistic or below, and then you multiply that by 2. When you multiply that by 2, you'll get the area that's also on the other side. Yeah, it goes both ways. So for this one, when we're doing a one-sided test, it never said if we're trying to calculate the area above the Z statistic or below. So it can either be simply half of the p-value, which is 0.22, which would be the area maybe above or below, but then you have to also figure out the complement area. So if 0.22, let's say, is the area under the Z statistic, you have to also figure out the area above the Z statistic. So it's either or, because they never specified in the question. So the possible VLs are either 0.22 or the complement of that adds up to 1, which is 0.78. So the answer is D. It's not just A, because you have to account for both possibilities. If they specified that what's the area under, then it'd be only like 0.22 or one of those. But you have to account for both possibilities.
Muted. Unmuted.
Does that make sense? Yes? Awesome. Fantastic. That's great. All right. So now we're at 6.6. See, the topics are not too long. We're already like speeding through. We're almost halfway. And we're an hour into the lecture. So now we're going to go over 1 and 4. So we've graded out 2 and 3 because we've already gone over those in great detail. I think, yeah, I've explained it pretty well. I hope so. So now we're going to go over 1 and 4. So we're going to go over how do you conclude a hypothesis test in general, and what's the significant level. So we've already know how to state the hypotheses and define the appropriate parameters, but we're mainly going to go over significance level and interpretation. So don't say what's wrong here if you know what it is. I just put this for fun. Don't say what's wrong yet. Once I ask, please answer and put a spoiler over it because I want everyone to figure this out. So with our significance level, as we've said in 0.5, it's determined by the researcher. So it can either be 0.01. Oh, Dork, I see you typing. Don't type what's wrong. If you want, you can put it as a spoiler, but no one click on it because I'm not explicitly asking yet what's wrong. So it can either be 0.01, 0.05, or 0.1. That's typically what your significance level is, what your alpha level is. This is called the significance level of the test. Simply put, this is the probability of rejecting the null hypothesis when it is true. This is also known as a type 1 error. We'll go more over those in the next topic, so that's coming really soon. But when we're using the alpha level, we usually want to have a low one, because if it's really high, we're going to have a really high probability of rejecting the null hypothesis when it is true. So the way you conclude your hypothesis test or your significance test, if the p-value that you obtain, type errors took me out to for real until I said type 2 fail to get it to. We'll go over, like, I've made a neat table for the errors, and I'll give you guys a very helpful acronym that my teacher taught me. It's really useful for figuring out the errors. I should have put it in the slides. I didn't. It's fine. So if your p-value is less than or equal to your significance level, you can say you can reject the null, which means that you have sufficient statistical evidence to support the alternate hypothesis, because that means that the probability of getting the sample statistic that you obtained due to chance is so low that it's statistically significant, and you can reject the null hypothesis, which means that your alternate hypothesis is true due to the statistical evidence that you obtained. Reject the null, yes. But if the p-value is greater than your significance level, not greater than equal, just greater, you accept the null, and that means you have insufficient statistical evidence to support the alternate hypothesis. Now, can anyone tell me what's wrong? Type it out and say, there is a very grave mistake I made here. Very grave. And if you make this, you will lose points. Alright, please, also refrain from getting polite language. Please don't use this kind of vulgar language. Small p don't. That works, but keep it to yourself. If it works on the exam, perfect. So yes, Dragonfire and Dork. You have the best explanation. If you accept null, you can't support HA. That's not really accurate. It's more that you never, ever, ever say accept null. Never, ever, ever, ever. At all. This is wrong. Significance tests, we never say accept null. Conclude null is true. You can't say the null is true. Why? Because in the beginning, we have an innocent before guilty mindset. We said we assumed already the null hypothesis is true, so you can't accept it. GPT yelled at me for doing this. I feel bad for never accepted. No, because we've already accepted him at the beginning. We already said, yeah, you're good to go. So why are we accepting him again? That's kind of redundant. So what you do is you reject or fail to reject null. Think of it like Shakespeare, to be or not to be. To reject or fail to reject. That's the question. It's not, or like Yoda, you either reject or fail to reject. So think of it like that. That can help you out. So think of Shakespeare. If you're thinking of which is the conclusion, think of Shakespeare. It's either reject or fail to reject. It's not reject or accept. No. It's not like opposite like that. It's the Shakespearean mentality. So that was what's wrong in that slide. Here are the p-value interpretations. So I kind of touched on this, but now we're going to go over it more. So if you have a small p-value, if you have a tiny p-value, if you have something really small, that means your observed test statistic is unusual, assuming the null hypothesis is true, which means that you have convincing statistical evidence for your alternate hypothesis, and the lower your p-value, the more convincing you have statistical evidence for your alternate hypothesis. But then unsmall p-values, or kind of big p-values, it means that your observed test statistic is not unusual, assuming your null hypothesis is true always and forever. It does not provide convincing statistical evidence for alternate hypothesis, because your test statistic is not unusual. It can happen due to chance. So there's a high chance that test statistics occurred due to chance, so it's not unusual. It's not atypical. So then the conclusions stem for our hypothesis when you're writing the conclusion. In our conclusion part, we say, because our p-value, put your p-value, is greater than or less than our significance level, we either reject if it's less than or fail to reject if it's greater. We do not have convincing statistical evidence to support that context as it applies to the proposed research question or claim. Right? So that's 6.6. So now we've done hypothesis tests in general, confidence intervals in general, but then specifically we've done for one population proportion. Now the next topics are going to go by a lot faster. Yeah. No, don't worry. Errors are easy. They're not too bad. This is a very short topic. This is kind of like a break from the intense, like, hypothesis test, significance test, we failed to reject. This is kind of like eases you into it. And this is really important for the exam, because you're going to probably ask about it when you get to power test for real. Yeah. Anyway, significance tests. Errors. You can make an error when you're doing a significance test. Shocking. So this table explains it all. So now you have your conclusion here, and so now you have which one is true, and then you have your conclusion. So, if your null hypothesis is true, and you fail to reject the null, so if it's true, but then you fail to reject it, that's a correct conclusion. That makes sense. If you say the alternate hypothesis is true, and then you reject the null, which means that you're saying that, yeah, the null, we have convincing evidence for the alternate, that's also a correct conclusion. But then the problem comes when you say that when you say the null is true, but then you reject it. Uh-oh, that's a problem. That's a type 1 error. That's a type 1 error. And then another problem, big uh-oh, is if the alternate hypothesis is true, but then you fail to reject null hypothesis. It's like, nah, I like null. I want to keep him true. I don't want to, like, reject him. But the alternate hypothesis is true? That's a big problem. That's a type 2 error. And that's pretty much it. So the way you remember these things, a good example is, think of it, let me transition to Discord. Let me make a window for that, because I'm just going to type this. I want the people who are watching the lecture to see this, because this is a really cool trick that I like. So, fail may lead to type 2. So, think of it as hot hat. So, a type 1, oh wait, it's not hot, it's hot hat. So, if the null is true, but then you reject it, that's T1. So, it's T1. And then if your alternate is true, but then you reject it, that's T2. So it's in the order of type 1, type 2. Remember the acronym HOT HAT. Very useful acronym. I still use it. I don't know these by heart. It's kind of hard to remember. If you use that acronym, you should be good to go. It's a very useful acronym. So it's HOT HAT. Right? That's it. That's all it is. HOT HAT. Does that acronym help you guys out? Or if you already knew it? Fire. Those are when it's true, right? So yeah, T means true. So if it's null is true, but then you reject, that's type 1. If alternate is true, but then you fail to reject null, that's a problem. So yeah, no problem. These acronyms are really useful for remembering the errors. See, they're not hard. Now we're going to go over more the technical side of things of these errors. So, as we said before, oh my god, I'm getting really tired. This is a lot of content to go through. I've gone through it in like an hour. We're actually on good pacing right now. Have to take a water break, sorry. Give me a second. I'm gonna continue just... Oh, this is a lot of stuff to explain. This is way more than Unit 3 or 1. It's very big units. Anyway, we press on. We're getting to the end. Alright? So, error probabilities. The significance level is the probability of making a type 1 error, assuming that the null is true. So that's your probability of you making a type 1 error. We already touched on what a type 1 error is. Then we get to something called the power. You'll never have to calculate power on the exam, usually. Maybe you might for like the investigative task, but on a regular FRQ, you won't. They usually give it to you. And it's the probability that a significance test will correctly reject null. Oh wow, there's a lot of typos here. I made these slides quite fast, but you get the point. It's the probability that a significance test correctly rejects the null when it is false. So it's the probability of finding convincing statistical evidence for the alternate hypothesis when the null is false. So when we assume it's true, but in reality it's false. That's just simply called, that's the fancy name called the power. That's the probability. The probability of a type 2 error is simply 1 minus the power. That's all it is. And it decreases when any of these occur given the other factors don't change. So if you increase the sample size, you decrease the probability of a type 2 error, which means you increase your power. If you increase the significance level, that also decreases the probability of a type 2 error. How do we calculate power? You don't need to know that. Don't worry. That is not on the exam. That is beyond the scope of this class of AP Stats. 1B for real. Yeah, beta. That's beta is power. But, like, just use power. You don't need beta. That's how it is on the CED. So the problem though with increasing the significance level is when you do that, since it's the probability of making a type 1 error, you increase the probability of making a type 1 error while decreasing the probability of making a type 2. So the best option is actually to increase the sample size. You can also decrease the standard error. We've touched on what the standard error is pretty thoroughly. If you decrease that, when you decrease the formula, that'll decrease your the probability of a type 2 error. And then the other thing is if the true parameter value is farther from the null. So the further the true parameter value is from our null, that will decrease the probability of type 2 error. And then whichever one is more consequential depends on your interpretation of the question. So you have to read the question and you have to figure out which one's more consequential depending on the context. So this kind of just depends on your logical thinking. And the consequences of a type 1 error influences decisions about the significance level. So if the consequence of a type 1 error is not that high, you can increase your significance level. So you can make it like 0.1, 0.2. If the consequences are not as severe as maybe the type 2 error and we want to focus on minimizing that as much as possible and we don't care about the consequence of a type 1 error. So it depends. We make a decision based on those factors. So now we're going to do a mini FRQ. This is mini because it won't take long. I cut out purposely some of the FRQ, a lot of it actually. So just read the question and describe what a type 1 error is and what a type 2 error is. That's all you need to do. So I'll give you guys a minute to do that. Reading the word. Yeah, the scenarios are really long. They're really annoying. But it's good training for the actual exam. Yeah, okay, perfect. I already said on the lecture calendar, I was just checking, that Unit 6 will probably be longer. The review will be longer than 2 hours because this unit is dense. As we already see, there's a lot of content to cover for this unit. It's really foundational, so we gotta take our time explaining and understanding because if you understand this unit, 7, 8, 9, light work, no reaction. So that's really good. Let's see how active general is. Just curious. You guys are solving the question, right? Just making sure. Yeah. Let me quickly go over the scoring guidelines because this is looks a little confusing. Just want to double check stuff. Go to question 2. Oh. 2003. Alright, stats. Let me see what's OBS is still sharing, I believe. Yeah. Scoring guidelines. Number 2. Let's see. Yeah. So yeah. I think, Sage, you mixed them up. Because type 1 error, like we said before, is the probability of rejecting the null when it's actually true. So when you assume that, it means when you assume that greater than 5% of the cars have a defect when it's actually less. So you have to switch them up. So I think Dork got it right. When less than 5% have the defect, so when the null is true, but then you find that more than that. So you make a type 1 error when the null is true, but then you find convincing statistical evidence that it's actually alternate that's true. And then type 2 is just the other way around, so that more, and in fact, more than 5% have the defect, but we find that less than 5% have the defect. What you did? It's not you assume, wait. No, you worded it wrong. It's not you're assuming automatically. No, because he said that the truth is the less than 5% of the cars that we find have the defect, but we actually find that more than 5% of the cars have the defect. You worded it a little badly, because it's not you assume. Yeah. Okay. But that makes sense, right? Dork's explanation is like, yeah, correct. That's how you interpret it. And then the consequences, Dragonfire described them. So it like recovers expenses when they shouldn't have, which, yeah, leads to a loss for the firm. And doesn't recover expenses when they should have, so they lose out the opportunity to make out money. So the type 1 error in this case is more consequential, because they lose money, but then type 2 error, they just lose out on the opportunity to make money. So that's just in terms of consequences, because this, in reality, the FRQ asks for the consequences, but I just ask you guys to do the type 1 and type 2 errors. But I just went over it now, because you'll often see that on the actual exam, in reality. Right? So let me just show Discord real quick. You open the chat, you can see. Yeah, Dork's explanation makes sense. That's just the answer here. And then these are like the consequences here, right? Presents but doesn't affect, yeah. Alright, but does that make sense to everyone? Yes? So yeah, on the test, you'll often be asked to like consequences or causes. Consequences. The right wording is like the consequences. You have to say, what are the consequences? It's not the causes. Causes is inaccurate. Right? Okay. Shall we move on? Know my answer or Dragonfire's answer? Your answer in terms of describing the errors is correct, but Dragonfire, what they did is they described the consequences. So, for this question, for what I'm asking, you just put what the type 1 and type 2 errors are. But on the actual FRQ, what it is you have to put the errors and then put the consequences, both. So it depends on the question. Okay, last thing before we go on. Just a friendly reminder to fill out the lecture feedback form, because I see a lot of people are leaving. There's only like you guys in here, but that's fine. But it's like everything making sense to you guys? Are the explanations good? Just need double check. Perfect. Awesome. Here. So now we're gonna go back to confidence intervals, but we're doing it for difference of 2 proportions. I'm gonna go a little faster because it's a different situation, but it's the same idea. It's the same calculations, same things, it's just a little bit different. Let's go. So now we're going to confidence intervals. Now you're either estimating the true population, which is just a one proportion situation, or the difference between 2 population proportions. So you sample 2 population proportions and then you determine the difference between them. So if there's a difference in the characteristics, so your null usually will be that, so, oh wait, no, that's hypothesis testing. Yeah. No, but like, yeah. By constructing an interval using a sample statistic. So now here, like I said, instead of estimating a desired population proportion from one population, you're estimating the difference of 2 population proportions from 2 separate populations for a particular character, such as, what's the difference between the amount of people who wear green shoes in Purplesville and Greensville? It'll probably be more in Greensville, But you get the idea. That was just a silly example, but that's the kind of thing you'll see on the MCQs and FRQs. That's the general approach. So first, I like to define what the scenario is and then go into the calculations and the conditions and stuff, so everything makes sense. So here, you take 2 separate random samples from 2 populations. Then you take 2 surveys, and then your sample proportion will be, because you're trying to determine the difference, not exactly so you can determine whether one's greater than the other. So you take your first sample proportion, subtract from the second sample proportion. That'll be your statistic, your point estimate. Confidence interval is simply that statistic plus minus your margin of error, which is your critical value times the standard error of that statistic. We went over this a lot. I think not going to clarify further. We're going to move on. Amount of statistic likely varies from the population parameter. So it's the same thing. See? Same exact thing, just a little bit different. The wording will be different and the conclusions you make will be different. So the formula is just this. You just simply take the first proportion, divide it by the sample size of that, and then you add it to that and you square root both. So this is the standard error formula. Again, the critical z-value is the same the way you calculate it, how many standard errors you're including in that confidence interval. So see, we're moving very fast because we already explained this very in depth earlier in the lecture. Right? I see someone left. It's fine. So now, it's very similar. Same thing, but it's a little bit different. Just a little bit. The conditions are a little bit different, but it's all the same idea. So first, you state the difference of population proportions you're trying to estimate and the confidence level. Name your inference method, check the conditions. Independence. Both samples have to be independent from one another, and they have to be both random samples, or it has to be a randomized experiment. And when you're sampling without replacement, both samples have to be less than 10% of the population. If it's an experiment, no need to check this at all, which is nice. Check normality of the samples, proportion sampling distribution difference. This is also called the large counts condition. I didn't mention this earlier, but that's what it's called. It's called the large counts condition. Number of successes for sample 1 and sample 2 are at least 5 or 10. It depends which is which. Usually you should say 10. And the number of failures for sample 1 and 2 are at least 5 or 10, which ensures both sample sizes are large enough. Then you do your calculations either by hand, we've seen this, or using the 2propzint function. Wait, how do we know if it's 5 or 10? Usually it says in the question, but I think it's usually best to say 10. Just use 10. Yeah, but I think it might vary in the question. But usually But I think 10 is better. That's what I usually use. And that's what you should probably just use on the exam. Yeah. So, the 2propzint function, the exact same thing. We're just going to go over this really quick. Let's see if I can get my webcam to work. 4,000th attempts. Do you guys think it's going to work? Probably not, right? Yeah. Oh. It's on. It's on right now. Okay, gotta... If you fail to meet one condition, do you continue with the question? You always continue. But usually the conditions will be true, but you still proceed. If in the case that one of the conditions is false, you still always proceed, but you have to say, an annotation, proceed with caution. Okay? So yeah. Okay. I think I've got it to work. For now. Save. You guys can see this, right? You guys can see? Yay! Awesome. Finally, we got it working. Hopefully in the video it's not laggy. No way. I'm gonna... Oh my god, if this stops working, I'm gonna crash out. So, I hope it's clear if I do this like that. So, when you're doing for 2propzint, you do second vars. No, not second vars. You do stat, and then you go to test, and you have so many tests you can choose from, but you choose 2propzint. You scroll down. No, it's 2propzint. Oh no, it's 2propzint. Yes, 2propzint here. Select this one, click it, and you see here a bunch of options. X1 is simply how many people in the first sample had that characteristic. X2 is the same thing, but for the second one. N1, N2 are your sample sizes. You do the confidence level, you click calculate, and then you'll get your confidence interval. That's it. That's all it is. All right? And then you conclude and interpret in context. We'll go over this right now in 6.9. So now we're in 6.9. This is just justifying claims based on a confidence interval and some interpretation stuff. So we've already went over this. Varies. Oh, hi, Omer. Yeah, okay. So, confidence interval. The interpretation is basically the same. but it's a little different, the wording. You'll see. So it's just, we are C% confident that the interval from this to this captures the true difference, not the true proportion, the true difference in proportions of, and then you put your context, right? And then your confidence level is in repeated sampling with the same sample size, approximately C% of confidence interval created will capture the true difference in population proportions. It won't capture the one population proportion, it'll capture the difference of them. We have to solve for confidence level given the standard error. Maybe. You might have to. Like in that MCQ you saw, you're probably going to have to. That was on the 2012 practice exam, so you're probably going to have to do that. But it will often be for one sample, for like for one true proportion estimating. But then when it comes to difference of proportions, you often won't need to calculate the sample size because there are two sample sizes, so they only do it for like one. Can you clarify the difference when to use prop Z test and prop Z interval? Prop Z test is for hypothesis testing. When they say construct a confidence interval, use Z interval. And and if it's one or two, it depends on if there's one sample or if there's two samples. Z test is for hypothesis testing. That's it. It's just for hypothesis testing. But then interval is for confidence intervals. Right? Does that make sense? No problem. And then you can use confidence intervals to prove and disprove claims like I said. So now we're on the last thing. This is just hypothesis test for difference of two population proportions. We're almost done. Took us a while to go through the content, but like on the lecture thingy, I said we might go over 2 hours because there's a lot of things to go over. So back to hypothesis testing. So now we're doing difference between population proportions. That's the new thing. This is the last idea, 6.10, 6.11. Use confident interval, perhaps, to help prove your hypothesis. Yeah, you might have to do that. You might actually have to do that. You might use a confidence interval to prove your hypothesis test. So wait, let me just go over some conclusions you can make real quick. So when it comes to difference of two proportions, if in your confidence interval it's only negative, that means that your, like, if it's like the first sample proportion minus the second sample proportion, if your confidence interval is only negative, that means that the second true proportion is greater than the first on average. But then if the first one, if it's P1 minus P2, if your confidence interval is only positive, that means the true proportion from the first population is greater than the second population. But if there is zero in that interval, that means that you cannot conclude anything, because since zero is in that interval, there's a chance that there is no difference at all between those two. So if you do a hypothesis test and you find that the null hypothesis is true, which is typically that there is no difference between the populations, and you have a confidence interval where zero is in the interval because there's negative values and the lower bound is negative and then the upper bound is positive, which means zero is in the interval, you can say that, yeah, the confidence interval helps prove our hypothesis test. So that's what Omer's trying to say. Yeah. So those are the conclusions you can make. So let me just type it in the chat real quick. So if it's negative, so like this is your scenario. So let's just say for difference of P1 minus P2. So if it's negative, that means P2 is greater than P1, right? But if it's positive, that means P1 is most likely greater than P2. But then if it's negative positive, zero is in your interval. Zero is in your interval, which means that there could be no difference. So P1 minus P2 could equal zero. Right? Does that make sense? This is conclusions for this. So you might have to use this when you're doing a hypothesis test, because they could intertwine. That's what I meant like earlier when I said these two things could like tie in together. Wouldn't this, depending on how big your negative? Not exactly, because if it's negative and positive, automatically there is zero into that interval. So if you think about it, even if it's negative 0.1, but then it's 0.001, zero is in your interval. Because if it's negative positive, zero is in your interval. It just makes sense. So because it's from a range negative to positive, so yeah, in that interval is zero. Yeah. All right. Moving on. Yeah. So we went over this, and In here, we've already went what a null hypothesis is, what an alternate hypothesis is. In here, the notation simply is it's either that the first proportion is equal to the second, the true proportions are equal, or you can denote it as this, P1 minus P2 equals 0. No difference between population proportions or an effect. But then for a one-sided notation for the alternate hypothesis, it's either that the first proportion is less than the second, or in other words, it's less than 0, and it's less than 0 because this is greater than 0, so therefore this is greater than this, so therefore their difference will be negative, so it's less than 0. Or it could be that the first population proportion is greater than the second, which means that, oh, you gotta go? Watch the recording. Oh, please fill out the lecture feedback form. I'm gonna send this one another time. Please send it here. Yeah, I'm still recording. So please fill out the lecture feedback form, and then you can leave. Yeah, thank you for letting me know when you're gonna go, because a lot of people just like dip out of the function. Anyway, back to what I was saying. So if it's P1, P2, and if it's just greater than 0, that means this is greater than this, so the difference is not negative. It's greater than 0. And then the two-sided notation is simply that the first proportion is not equal to the second. So the difference is not 0, but it could either be that the first population proportion is greater than the second, or the other way around. So that's your notations for the hypothesis. So the procedure name is simply two sample z-test for a difference between two population proportions. It's a mouthful, but yeah. So this time we have access to 1 and 2, but then we unlock 3 and 4 in 6.11 because that's how it is in the CED. So you do your learn how to do our calculations in 6.11, and then you learn how to conclude and interpret in 6.11. So first, you state your hypothesis, significance level, define the appropriate parameters. So you define your parameters. What I mean by that is if you put P1 is this, you have to say what is P1. Where you can say where P1 is the proportion of people who wear green shoes in Greensville. And then P2 is the proportion of people who wear green shoes in Purplesville. For example, that's how you would do it. The independence is, you need to check for independence, 2 independent random samples or randomized experiments. Both samples have to be less than 10% of their populations. You don't need to check this if it's a randomized experiment. You have to check that the sampling distributions of both sample proportions are normal. So in this case, it's a little bit of a special situation because when you're checking for if you're the number of successes or the number of failures, you have to check the pooled proportion. So you have to calculate your pooled proportion, and I wrote it wrong here. I'm really sorry. I'll fix that. So it's x1, x2, which is how many people in both populations have a specific characteristic that you're trying to determine, and these are your sample sizes. So you add them up to get your combined proportion. And when you're checking for successes in both population proportions, you first check that the first sample size times your combined proportion, and your second sample size times your combined proportion, in addition to the number of failures, which will simply be your first sample size times your combined proportion, or 1 minus your combined proportion, and then the same thing with your second sample size. But all of those things have to be at least 10 or 5, and that's the large counts condition. So with that, we're just going to cover a quick practice MCQ. This is just you're given a study, what is the appropriate null hypothesis for this study? Oh, by the way, did my explanation of this make sense? Yes? Alright, yes. So do this one. And yeah, we're almost done here. So just do this practice MCQ. Let me see if the answer is what I think it is. Yeah, it's that. Let's see if you guys are on the same page for now. Okay. Everyone vote, please. Everyone voted. And there's some difference. Okay, let's now just clear up the misconception. The answer is B, right? Why is it B? Can someone who chose B explain why it's B? Why is the answer B? Yes. Good job. Null in terms of two population population. In this case, it's means, but you get the idea. It's in this case, it's just that the difference between the two means or the two proportions is 0. That there is no difference between them. That's always your null. It's the same for both. It's never that it's different from the average. They're not different. Your null is always that they're the same. No. It's the wrong unit, but I just pulled it out because I pulled out this MCQ because, again, Unit 6 is kind of introducing significance tests, so you can still use this MCQ. It's good practice. Even if you don't know what Unit 8 is, you can still get this right if you know what significance tests are in general. If you know that general rule of thumb. If you just know your stuff, know your concepts. Thought what they said was the null. Yeah, the null is, in this case, if it's difference of two like proportions or means, it's always that they're equal. Did that explanation make sense? We're on the last topic. We're almost done. And then we're going to do an FRQ, Q&A, and we're done. Ready? Are we ready to move on? Everyone? You might leave for FRQ? I see. Why? You should stay. But if you really have to go, then that's fine. Don't worry about it. So now here, we have to do our calculations or interpret in context. So in our calculations, like we said, standardized test statistic, z-test statistic for proportions. The statistic is the difference between the sample proportions. The parameter is 0, which means no difference. Our standard error is just this formula here. Whatever that is, it doesn't really matter. And it is always the combined proportion. Because here, P1 and P2 are assumed to be equal because that's our null. So we use combined proportion, so we calculate that here. Standardized test statistic is over here. And then you calculate your p-value, which is simply your area on the standard normal curve. So where the difference of the two sample proportions lie on our standard normal curve. And then you use normal CDF to calculate the area. We already went over this in great detail. So then, yeah, your significance level is simply determined by researcher. It's either 0.01, 0.05, or 0.1. That's the significance level of the test. Is that one of the formulas we are allowed to have on the exam? All of the formulas I show, yeah, these are all on the booklet, the formula booklet. Don't worry. You don't have to memorize these. Yeah, exactly. And you don't have to memorize the exact formula for a standardized test statistics for these situations because you can construct it yourself. You're welcome. You're given all the formulas and you can build them yourself using this general, yeah, it'd be a nightmare if you have to memorize this. Yeah, I wouldn't wish that on my worst enemy. This is awful. But that's why calculators exist. So for our 2-prop z-test, actually, let me turn on my webcam. We're gonna do some more webcam action, and hopefully goes well. Hold on. Okay, so here, let's exit this. Let's go to okay. Let me raise this a little bit. Make sure you guys can see. So your stat tests. Scroll all the way down to 2-prop. Zient. Okay, I'm trying to. Yeah, and then of course you put here x1, how many people have the shared characteristic in your first population, x2 for the second population, and then you put your sample sizes, you put your confidence level. Oh no, this is int. This is not test. Whoops. T-test, not T-test, Z-test. Whoopsie daisy. That was a little bit of a blunder on my part. 2-prop z-test. Perfect. So it's the same thing, except you also have to put here what's your alternative. So is the first proportion not equal to? So are they different? Or is it less or is it greater than? So like if their difference is... So you assume their difference is 0, but what's your alternative? Is your alternative that like they're not equal, or is one less or one greater? So you have to put, depending on the situation, click calculate, and then it'll give you. So it gave me an error because I didn't put them correctly, but if you do the correct situation, it should give you all of that. You typically do that on an FRQ, but you still need to know how your formulas work, because on an MCQ, they might, like, what's the Z statistic? What's the formula for that? And then you're going to have to choose a choice based on that. So you have to know how to still do it by hand. It's still, you know, good to know, because for the MCQs mainly. But for FRQs, you should just use the calculator because it's much faster that way. So again, significance level, probability of rejecting null when it's true. If p-value is less, you reject null. Sufficient statistical evidence. We know all of this. And finally, we're going to end off with our conclusion stem. So because our p-value is greater or less than significance level, we fail to reject. We already know the conclusion. Based on that, we have or do not have convincing statistical evidence to support that context as it applies to the proposed research question. Do type 1, type 2 errors still apply here? Yes, they can. So you can say, oh, we assume that these two, that Greensville and Purplesville, both the amount of people, the proportion of the people that wear green shoes there, we assume, for example, that it is equal when in reality it isn't, where maybe Greenville wears more or Purpleville wears more. That's like a type 1 error. Type 2 would be like, you assume that there is a difference when there actually isn't a difference. Yeah? So type 1 and type 2 errors still can apply in this situation. Okay, last MCQ, and then we'll go on to one FRQ that you guys will choose. Depending on, like, you know, you guys get to choose. Okay, so solve this. Someone make a poll. Dork or... Okay, thank you. So, yeah, I'm giving you guys some time to choose. Since there's 4 people, I expect everyone to vote and choose an answer. If you guys want, I can go to the explanation right away if you guys are struggling. Because this is a little bit of an annoying MCQ. But if you guys can solve it, that's fine. Okay. One sec. Yeah. It's good to also, yeah, make sure you take the time to think about this stuff and know how to answer. Because you got to use your brain to actually solve the question. If the answer is given to you on a silver platter, it's not really helpful for anyone. Two votes. I see. This is a confusing MCQ, so no worries at all. Oh, by the way, I forgot to say this earlier, but you can feel free to check your notes if you need to. Just saying. You can feel free. Feel free to do that. I'm gonna wait for everyone else to vote. Let me switch to Discord so that this isn't really mundane just looking at the slides. Alright, open the chat. Go back to slides. Yeah, I just want to show like what people have voted and stuff like that. For the people who haven't voted, do you guys want me to go to solve, or are you guys still trying to figure out something? Okay, 3 people have voted. Wow. Guys, I'm sorry. None of you got that right. But it's okay. It's fine. Don't worry about it. It's completely fine. Alright? This is a difficult MCQ. It's pretty difficult. But I'm going to go through it step by step so we make sure we understand what this is. The wording is awful. Garbage, trash. I will admit that to you. Just to make you guys feel better, the wording is so bad. So bad. Let's go through this. So, we're going to go through it in depth because everyone got it wrong. A large number of randomized experiments were conducted. So we have a bunch of experiments to determine whether taking a particular drug regularly would decrease the chance of getting a certain disease. So, right, we have an experimental situation. So now for each of the experiments, the drug effect, so now this is really important, we're measuring the drug effect, is the difference between the proportion of people taking the drug to the people who got the disease and the proportion of people taking the placebo who got the disease. So we automatically see here, this is a difference of two proportions situation. This is like a difference, whether it's a confidence interval or a hypothesis test. So it's a difference between those. So it's a difference between the proportion of the people taking the drug got the disease and the proportion of people taking placebo who got the disease. If the drug had no effect whatsoever, which means that there is no difference between the people who took the drug and the people who took the placebo. So there is no difference. There is the people who took the drug had more, that means there is no effect. There is no difference between them. So if there's no difference, which of the following experimental results can we anticipate? So automatically, 1 and 3 we'll go over in a bit, but 2 we can automatically say this is right. Because there will be an equal amount of experiments showing positive and negative values. Since they're equal, when you subtract them, the difference will be 0. We always assume 0 correct for 2 proportion. Yes, you always assume 0 for the difference. The difference is 0 when you're doing difference of 2 proportions, whether it's a confidence interval or you're doing like a hypothesis test, whatever. You always assume the difference is 0. So there will be an equal amount of experiments showing positive and negative. So when you subtract them, the difference is 0. So now let's go over 1. P-values will be greater than 0.05 for about 95% of experiments. Now, this is a little weird, but if the p-value is 0. Okay, so a p-value of 0.05 means that since we're saying p-values will be greater than 0.05, we can assume that in this scenario, the significance level is 0.05. Since the significance level is 0.05, that means the probability of making a type 1 error, which means the probability of saying, alternate is true when actually null is always true, that's a type 1 error. But the opposite of that, which is making a correct conclusion, the opposite probability, which is the probability of making a correct conclusion, saying that null, we fail to reject null when null is actually true, the correct conclusion is simply 1 minus the significance level. So that means the probability of making a correct conclusion that there is no difference. And in this scenario, we're saying that the null is that there is no difference. And if the p-values are greater than 0.05, which are our significance level, that means we fail to reject the null, which means that the probability of making a correct conclusion in that regard is 0.95, which is 95%. Which means that for 95% of our experiments, we'll make a correct conclusion, but then for 5%, we'll make a type 1 error. Right? So 1 is right. Does that make sense? Okay? Yes. Yeah, it's a little confusing, so if you don't get it, it's fine. On your first try. Might take a bit to understand. 95%, it'll be no error. Yes, because they don't say this is the significance level, but when they say p-values will be greater than this value, since they're basing it off of that, the significance level is this value here, 0.05. So 0.05 is the probability of making a type 1 error, but the probability of making a correct conclusion, which is failing to reject the null, is 95% of the time. And it applies in this situation because we're saying if the drug actually had no effect whatsoever. So if the correct conclusion is the null, and we fail to reject that, happens about 95% of the time. Right? So yeah. That's pretty much, does that make sense? So I think, now 3. I is the hardest to understand. I think 3 is a little easier. So this is just an interpretation of the confidence intervals. So when 95% confidence intervals for the population drug effect are constructed, right? So when you construct a 95% confidence interval, when there's 0 in that, that means that there is a chance that the drug has no effect whatsoever. So if it's in there, that's 0. So the true value, the true difference is 0 because we're saying the drug had no effect whatsoever, so there is no difference in between them. So when we're looking at the interpretation, remember, of a confidence interval, we're saying that or confidence level, we're saying about confidence level 9% of the time, it will capture the true proportion or difference of proportions. So in this case, the true difference of proportions is 0. So when we're constructing 95% confidence intervals, there will be a 95% of the time we will capture 0, which is our true parameter, right? So that means I and 2 and 3 are all correct, but not 3. What do you not understand? I'm gonna make it very clear. It's fine, don't worry, I'll explain it again. Okay, you do now? Perfect. Does everyone know why all 3 of them are correct? Does that make sense to everyone? Yes? Perfect. Yes. Yay. Alright, that's it. We're done with the content. Now we're gonna do FRQs. So, we have 4 FRQs here that we can choose. That you guys can choose. You guys get to choose which one we do. So I've handpicked the FRQs we can do. We can either do an FRQ for the confidence interval for one population proportion, a confidence interval for the difference of 2 population proportions, or we can do hypothesis tests. We can do a hypothesis test for a population proportion or difference of 2. So I've selected the FRQs, you can do them. One of the hypothesis ones, let's do a poll. Someone do a poll and just vote 1, 2, 3, 4. And it's in the order of that. So if you vote 1, yeah, which one? Which FRQ would you guys like to do? Everyone must vote. Oh, there's a tie. 1 and 2, 1 and 3. How about this? Do you guys want to... Oh, there's still... Okay. Everyone lock in your votes. Is that it? Don't change your vote a lot. I want to do an FRQ. Three wins. We're doing a hypothesis test for the difference of population proportions. So now it's going to take me a bit to set this up. I'm just going to modify the slides real quick. I'm going to change the screen to Discord. And I'm just going to do my thing a little bit. It's going to take a bit of time. But I'm going to add them to the slides and stuff and whatnot. So this will be the final version. Okay. Okay. It's a pretty decently easy effort. It's very straightforward, which is awesome. But yeah, this shouldn't take too long. Okay, let's just duplicate slide, and then we'll go over the solutions together. All right, how about this? You guys solve it, and then we'll go over it together. So I'll go through the steps together, and I'll solve it with you guys. We're not gonna go over the solutions. I'll solve it with you guys because that'd be easier. Because the solutions will not be the best, but you guys can still check the solutions to make sure if I'm doing everything right. Okay, let me add those bad boy FRQs to the slides. All right. Practice FRQ. All right. Is it still working? Oh wait, actually let me fix this. Let me scroll down in the chat so that it's okay. I'm almost done with this. Put it here. And alright. I've set it up. Now we do it. You guys do it first, and then we do it together as a class. Okay. Let's change my screen. Oh. Okay. Here we go. Let's do it. Can you guys see the screen? Start solving. Alright. I'm gonna set a timer for like 15 minutes for you guys to solve this. And I'm gonna solve it as well while you guys are solving, but I'm just gonna be right back.
Muted. Unmuted.
Okay, I'm back. I'm gonna take the time to solve this as well, so that we don't waste time and I like solve it like after you guys solve it. So like I'll solve it with you guys together. All right. Okay. All right, I'm solving this. To the person who just joined, we're doing a practice FRQ. I'll go over it with everyone in like 11 minutes. I'm also solving it, and everyone in the lecture is also solving it. So you can take the time to solve it if you want, and then I'll go over it like in like 11 minutes. By the way, I'm doing all the working as well. I'm gonna do all the working, and I'll show you guys like how like it looks like if you do the work. We need to show our part for part A on the actual test. Oh yes, absolutely. If you're gonna use your calculator, write down what calculator function you use and then input like accordingly. So you gotta do that. But no work for part B, no, because you base it off of part A. How would you show inputs? Yes, you do the normal CDF input, but like for each input, you say like what that input is. So like if it's the lower bound or the upper bound, you gotta like annotate that. Otherwise, you won't get full credits. Would we have to label the number? Yes. Yes, you do. That's what I said. Do we have to write the formula? No. If you're using a calculator, just show the calculator function. For context, I'm at the calculation part, me personally. I'm doing the calculations. I'm checking my solutions in the scoring guidelines, just to make sure I give you guys a correct explanation. Preferably you guys try to solve it on your own. It's this is the fourth. Are you guys, did you guys solve everything? Yes? Okay, you did. What about everyone else? Yeah, almost? You? Okay, take your time. I'm also trying to solve, by the way. So I'm not just like letting you guys do, because I'm going to show you guys what I do. Okay. No, dude, it's okay. It's all good practice. You can see. Don't worry, don't worry, don't worry. Will we do everything else, or is this it? What do you mean? Oh, will we do anything else? Oh, no, this is it. We're just going to go over the solutions for the FRQ that I do, and then we're going to do a 15-minute Q&A, or if you guys even have any questions. If we don't, we can just end the lecture. So we're at the cusp. We're almost done. We're almost there, guys. Don't worry. Okay, I finished part A. Sage, are you done or almost? Okay. Okay. Let's now go over it together. So, you guys can check the solutions now if you want to. This is, the 2021 FRQ for AP Stats, and it's the fourth question. So you can check the scoring guidelines, but I'm gonna go over my solution. So my handwriting is not the best, but, it's fine. It's not gonna kill anyone. Okay, let me lower my webcam. Show this. If it works even. Okay, this has to work. Oh, perfect. Okay, can you guys see this? Yeah? Okay, let me move this back. Just to make sure you guys can see everything. Okay. So now, we see here that when we're doing all of this, so this is part A. So we start off with the sample proportion. I'm dead now due to said handwriting. I'm sorry. I'm really sorry. This is really bad handwriting. I know. So, we see here, first we go over the sample proportion. We calculate the sample proportion, and because it's 0.42, we know our alternate is going to be that greater than 40% placed placed an order after receiving a $10 coupon. But because because the manager is saying that more than 40%, we can say that our null is equal to 40%, right? And we said that our significance level is 0.05 as it's defined in the question. If it's not defined in the question, you can say like 0.01, but you can always use 0.05. And then P, this thing just means the true proportion of past customers that place an order if they are offered $10 off on their next purchase. So if they receive a $10 coupon, will they place an order? So we're saying that P is the true proportion of customers that do that. That place an order if they receive a coupon, right? And then this is our like stating. When we state our parameters and stuff like that, now we have to check our conditions and do the planning. So we say we're going to conduct a one sample z-test for P. You can say for one proportion, but you can just say, because we already defined the parameter, you can just say P if all conditions are met. Since this is not an experiment, you have to check all three conditions. You have to check that first, it's a random sample, as you can see here. Then you have to check, and it is a random sample, 90 customers were selected at random. The 10% condition, 90, less than 90 of 10% of all customers. When they don't give the population of customers usually is really large. So we can assume safely that less than 90, that 90 is customers is less than 10% of all customers, right? So do those parts make sense so far? Let's see if I can just adjust this to show you guys everything else. So, yeah. Let me raise it a little bit so you guys can try to see. You guys can see this, right? You don't need to read this. This is terrible. I'm just gonna say. But can you guys see this and everything? Guys? Hello? Not gonna lie, not really. No, the last bit. You can't see the last bit? I see. Not the bottom half, yeah. How about this? This is a little bit weird. Okay. Wait, let me try this. Let me flip the camera. Okay. This should work now. Oh no, it's like now just upside down. If I do this like that. Oh no. Whoops. And I lost it. Oh my god. I have no idea where it went. Oh, it's there. Okay, here. Oh, you guys can't still see that? Okay. Well, I tried. My bad. It's a little hard to do this, but I just said for the large counts, like you just multiply n, the sample size, by the null, which we said is 0.4. You multiply those, you get 36, which is like greater than or equal to 10. And then you do the same, but like for the opposite, 1 minus the null, and then you get 54 is greater than or equal to 10. So both these, you check them, and you realize that, yeah, large counts is met, random sample 10% condition is met, so you can conduct the hypothesis test. So now, I'm just going to do my calculator work. You guys can see my face. It's fine. Doesn't matter. It's fine. So now, wait. So now what you do is you go to stats, you go to tests, and then you go to one prop z-test. Not z into z-test, right? And then what you do is simply input everything. So we know that our null is 0.4. Let me raise this a little bit so you guys can see better. You put x, that is 38. That's the amount of people that in our sample that bought the made a purchase with the coupon. N is 90, which is our sample size, and we're saying that the true parameter is greater than 0.4, so it's greater than the null. We calculate. What we get is we get a p-value of 0.33, and that's greater than 0.05, and because of that, we fail to reject the null, which means we don't have convincing statistical evidence that greater than 40% of customers who are offered a $10 coupon will make a purchase. So we don't have convincing statistical evidence that more than 40% will do that. And our Z statistic is 0.43, and you always have to write that when you're doing this kind of FRQ, right? Does that make sense to everyone? To you guys? Yes? Okay. This now should be a little clearer. So I didn't finish writing it. I lost my pencil. I found it. So, here what I'm writing is, because we failed to reject null, we may have made a type 2 error. Where basically, when we reject the null, we're rejecting it, we're failing to reject it, when in reality, the alternate hypothesis might be true. So when an alternate is true, but then you fail to reject null, which means you're kind of rejecting the alternate, that means you made a type 2 error. Hot hat, remember? So we write the acronym here. Hot hat. Right? This here, if our alternate is true, but we fail to reject null, which means we stay with null, this is a type 2 error. Of course, no problem. There's only 2 people left. Type 2. Wait, don't forget to fill out the feedback form. Wait, let me send it. Please tell me you didn't already leave. Okay, here. Please fill out the feedback form and then you can leave. Thank you so much for staying. So now we have a type 2 error here. And the consequence of that, right? Because the customer is because the manager is trying to offer $10 to get more people to purchase, the consequence of that is she won't continue, or they won't continue offering $10 off of their next purchase. So they're going to lose out on getting more customers to like purchase stuff, right? Does that make sense? So let me just go back to the lecture. It's not showing the slides. That's annoying. Yeah, fix that. Okay. Here. Okay. Let me just check the solutions. I'm going to open up the solutions as well for you guys to see. Hold on. E or A or B. Let's see if this is correct. So I'm just going to open this up here. Let me change the window of OBS. Hold on. It's showing here. Oh, no, it's no longer showing. Here. Can you guys see this? Can you guys see my screen? Yes? Okay. Alright, let me just put OBS on the other end of the screen. And minimize this. Yeah? Okay. So yeah, we see here that because null hypothesis was not rejected, type 2 error could have been made. Type 2 error occurs when the null hypothesis is false and not rejected. In this case, type 2 error, by failing to reject this, would result that would place an order within 30 days after for $10, when in fact more than 40% would do so. Consequently, the manager might decide not to do this, would result in more than 40% of customers making a purchase within 30 days. So you see here, you have to explain the full context, and you simply explain the consequence of doing such. So the consequence is just you lose out on getting more customers to purchase stuff. That's the consequence. And you have to define what a type 2 error is and stuff like that. So you see here, states type 2 error could have been made, provides reasonable interpretation by including a minimum of those who place an order and stuff like that. So you have to also be very specific in your explanation, and if you're not specific enough, you could not earn all of the points. So that's it. Does that make sense to everyone? Yes? Okay. And that's that. That's the lecture done. Hold on. Let me put OBS back where it's meant to be. So that's that done. Now, some extra review sources for you guys you could use. You can use AP Classroom. Great for MCQs and FRQs. You know what you're going to get. It's from College Board. You can use 5Hive's website, 5hive.org. They have great review sources. You can use, you can do their practice tests. When the articles come out, you could read those. And you can also use College Board's review playlist. I haven't personally checked that out, so I wouldn't really endorse it. But Advanced Kentucky, I haven't also checked that out either. But, you know, it has some good math videos and CS videos in general for those AP classes. And it has videos for AP stats, so you could use those for extra review. The Khan Academy has some very good MCQs practice. But then in terms of FRQ questions, exam questions, you can use the past exam questions. In terms of FRQs, you use your past FRQs are your best friend here, right? So again, last thing I want to say Please fill out the lecture survey. Thank you guys, you two, for staying towards the end. A lot of people left, and I really appreciate you guys for staying. That's really great of you. That's really awesome. So yeah, please fill out the feedback form, and now we're gonna do a Q&A. I'm allocating 15 minutes for this, but I don't think you guys seem to have like a lot of questions. I think you guys are. We've been here for like 2 hours and a half, and I think you guys kind of just, yeah. How was your day? It's okay. It's 12 a.m. right now. I've been here for 2.5 hours, but it's good. It's good stuff. It's all good stuff. Let me change the screen to Discord here. Yeah, time zones are really different, man, for sure. That's a fact. If you don't have any questions, I can just end the lecture. Tater, do you have any questions? No questions from me? What about you, Tater? Don't forget to fill out the feedback form, please, before you leave. And that's it. I hope this was a very good review. Do you guys feel like it was a good review? Overall? Of course. No problem. Awesome. That's really good to hear. You put that on the lecture feedback form. Make sure you say that, like, it helped out a lot and stuff like that. So just give your feedback. To be completely honest, it's anonymous. I feel like there were some key details you mentioned. What do you mean? I didn't know before. So that's good. Good that I helped you out and stuff like that. That's great to hear. Awesome. I like the hot hat. Yeah, it's a really good trick. Really helpful. Really useful. Like the null would be 0 in 2 proportion. Yeah, and other things I can't think of right now. But yeah, I'm going to post the lecture video right now and the lecture slides as well. I might have to fix up the lecture slides because it's a bit whack. There are some like inconsistencies in there. But overall, I think it's pretty good. You can use the lecture video, of course, as another review source. This is not really an additional thing, but you can use it. But yeah, if you guys don't have any questions, then that's it. Oh, yeah, like I said, yeah, I'm happy you guys learned some new stuff. Happy it helped you guys out. And I hope you guys get 4s and 5s on the national exam. When is your CSA review? Saturday and Sunday. It's gonna be really annoying to have to make those lecture guides, but I'll push through. Don't worry, I know how to grind. I've given 3 lectures in the past 3 days. Are there any other sources you suggest besides Khan to practice? For FRQs, the past exam FRQs are a really good source. What unit? 3 and 4. 3 Saturday, 4 on Sunday. So yes, those 2. Big boy units. They're the most weighted and they're very foundational. Nicholas is gonna do the a combined unit 6 and 7 review. Like, I think next Saturday. I see when I might come by even though I'm not taking, just to review Java. Cool. Go for it, man. Yeah, it's good to support me and stuff like that. More traction. It's useful. It's cool. For real, yeah. More aura. Yeah, you could think of it that way. But yeah, you guys don't have any more questions? Okay, I'm gonna go. All right. See ya. You filled out the lecture feedback form, right? You guys filled it out? Just double checking, making sure. Did like 5 minutes ago? Perfect. Tater, did you? Awesome. That's it. You guys are awesome. This was really good. This was really fun, and it helped out. Wow. To the person you just joined, you just missed all of it. I just finished, but this is recorded and I'm gonna post it, so yeah. Don't worry. If you have any questions for me, you can ask like right now before I stop the recording and leave. That's it. To the person who just joined, Oops. Let's stop sharing. All right. To everyone who's watching the recording live, thank you so much for watching all the way through. I hope this helped you out a lot and that you learned a couple new things. You can use a Turbo Learn to put this lecture in, and I hope AI can like summarize it and stuff like that if you can't be bothered watching the whole 2.5 hours. But yeah, that's pretty much it. Hope you guys benefited, and that's about it. Yeah. Bye.